we're looking at intersections of lines in 2-space, which is familiar from grade 10, and 3-space, which is kind of new. When we were working in 2-space, everything was relatively straightforward, okay? So you could have lines, and those lines could intersect, and we knew how to find the point of intersection using the methods of elimination or substitution. I prefer elimination. So here's the example. L1's positive slope, L2's negative slope. Unless they're parallel, they're going to intersect. They have to, okay? Here's equation 1. Here's equation 2. We need to manipulate them so that we can eliminate one of the variables. Unfortunately, this is super easy to eliminate one of the variables the way it's set up, kind of on purpose. I don't have to multiply equation 1 or equation 2 or both by any number to get this to work. I can just add equation 1 to equation 2, and I get 2x minus 6 equals 0. So I get x is equal to 3. Okay. By elimination, I found out that x is equal to 3. And of course, what I'm going to do is take that 3 and substitute it for x and figure out what y is. In this case, oh my goodness, y is just ugly. So y is like, if I did the math on this correctly, which I almost never do, this is 3 minus 4, that's 1, it's like 1/2. Okay. So there's an example of an elimination. Morgan, did I do everything right or did I make a mistake? Let me know. Good. I accept your silence as acquiescence to the truth.
I said it should be good.
Okay. Here's a second situation where we have two lines that are parallel in R2. By inspection, we can see that the normal vectors, just looking at the scalar version, the normal vector is 1, -2 for both of these. They're headed both in the same direction, okay? We could get a similar situation if this was 2x minus 4y or 6x minus 12y. We would have the same thing, okay? Anyways, when we do elimination on this, so if I did equation 1 minus equation 3, I would get, this would all eliminate, except for this number down here. This would be 2 equals 0, which is never, ever true. Never true. Okay, 2 equals 0 is just not true for any value of x and y. And so these do not intersect. This is the only situation in 2-space where lines don't intersect. The last example I can get in 2-space is where the lines are coincident. Okay, so I've got line 4 lying on line 1. All of the points in line 4 are the same as the points in line 1. Basically, here's equation 1, here's equation 4. I can just see that essentially number 4 is equation 1 multiplied by -1. When I go to add these together, I get 0x plus 0y plus 0 equals 0, okay? This one, always true. Any value of x and y makes that expression true, and so those lines are coincident. So I actually have this little test I can do to see if the lines are coincident, if they're parallel, or if they're intersecting. So that was good old 2-space, pretty easy to deal with. We're moving into 3-space. We still have this situation. We can have lines that intersect. We can have lines that are parallel to each other. We can have lines that are the same as each other, but we get this last example. And that is the case of skew lines. All right, so I'm gonna look at skew lines for a second, okay? Ho-ho, so here we go. We look at these two lines and we say, oh, look, those lines do intersect. Anyways, if we rotate it, the way you can rotate the GeoGebra sketch, you can see that actually in 3-space, they don't intersect. Not every point lies on that line, okay? So if we were looking at the x and y plane, so looking down from above, we would think these two lines intersect. But if we rotate the whole thing, we can see actually they do not intersect This makes them what's known as skew lines. Okay, they're not parallel, coincident. They do not intersect, so they're skew. So that's our third example. So we can get skew lines.
Does skew mean that they exactly are like on top of each other?
So the question is, does skew mean they're exactly on top of each other? No, it just means they're running through 3 space, and they never cross. Okay, so there goes. Oh my goodness, that doesn't look very good at all.
Skew lines are 2 lines that never cross in 3 space.
They never intersect in 3 space. Okay, from certain perspectives, they might cross, but they never actually occupy exactly the same point. Okay, so we will not find any points that are common between skew lines. And we need to keep that in mind when we're answering, when we're trying to find points of intersection. Okay, so here we go. Here's our vector equation of the line. We have a position vector, and then we have a direction vector. We multiply it by some parameter s. So if s is any real number, we can get anywhere on a line. That's defined by that. We have a second way that we define these lines, and that is known as the parametric equation. Okay, and so here's line 1 in parametric form. So I'm going to do the x. So 2 minus 3s is my x coordinate. Okay, and it's based on the value of the parameter s. What is my y coordinate? What's the formula for my y coordinate?
1 minus 2s, or 1 plus 2s.
1 plus 2s is my y. And what is the formula for my z coordinate here?
2 plus 2s.
2 plus 2s. Very good. Okay. And we're introduced to a new version of the line. So it is the symmetric equation. Okay. So I just rearranged this. Basically, I am isolating y in each case. Sorry, I am isolating the s. So I'm isolating the parameter, and then I'm going to wind up with 3 expressions that are all equal to s. So what does this x expression become if I isolate the s? Can you tell me, Morgan?
Can you move your camera a little bit to the left so I can?
Yeah, okay. Then I'll write them over here for a second. Okay. So I'll do the first one. X minus 2 over negative 3 is equal to s.
And then is that 1 plus? Okay, wait, hold on. I'm trying to look at the equation. So it's y minus 1 divided by 2.
Y minus 1 divided by 2 is equal to s. Very good. And then the last one.
Z minus 2 divided by 2.
Z minus 2 divided by 2 is also equal to s. Yes. So now I have my symmetric equations of this line. So I have 3 different ways I can express it. I'm just going to write the symmetric down here for a second. And I can write them like this. I know that you guys can't see them because they're covered up right now. I can just write them
all equal to each other.
All equal to each other, and then I can just ignore my s. Okay? So I've got them written down there. Hopefully we can refer back to them as we try and figure out if these lines intersect. Now, and the answer is yes, they intersect. These ones do. But we need to be cognizant that quite often they do not. Okay, so parametric form, x equals, Johnny. Negative 3 plus t, right? Start at negative 3, go over t times 1 unit. Y is equal to 1 plus t, okay? And z is equal to negative 2 plus 3t. And if I convert these all to symmetric form, which is easy peasy, t is equal to x plus 3. T is also equal to y minus 1. And t is equal to z plus 2 divided by 3. Okay, so there's my symmetric form of the line for the second line. All right. So always remember at an intersection, X, Y, and that's just, yeah, that's the inclusive and. The X and the Y and the Z coordinates are equal. Okay, so the X and the Y and the Z coordinates are always going to be equal at a point of intersection. Okay, here's method 1. We're just going to look at 2 methods really quickly. So method 1, we're going to try and find the value of the parameter s where L1 and L2 intersect. Okay? So my x coordinate here, so 2 minus 3s, has to be equal to my x coordinate over here, which is negative 3 plus t. All right. So this is my x coordinate. So let's
Why
turn
do we
this
have to have s's and t's? Like, did we have to do that?
We actually do using this method, right? Because this is the x coordinate for the first line. This is the x coordinate for the second line. And I know what you're thinking. We've mixed in 2 different parameters now. How are we going to fix that? Well, you just watch. It's going to be okay. All right. Good so far. Now we're also going to say that our y's are equal to each other. Now, just a minute. Do I want to do it this way? No. I'm going to change this into negative 3s minus t is equal to 0, and I'm going to make that my equation 1. So I've just rearranged it into this nice scalar form. Okay. Now, our y coordinates have to be the same as well. Okay. So this was x has to be equal to x. Now we're going to do y has to be equal to y. So 1 plus 2s has to be equal to a 1 plus t. And now we're going to rearrange this into the scalar form again, 1 minus t equals 0. And I'm going to call this equation 2. Okay. So the good news is we have 2 equations and we have 2 unknowns. So this uncomfortable situation where we had 2 parameters mixed up, we can fix using elimination. Okay. So here's equation 1. I'm going to write equation 2 underneath it. 2s minus t 0. All right. Good. What should I do?
You can just pick up the t's, can't you? Like
Yeah,
if it's subtract by.
Exactly. It looks to me like the easiest thing to do is going to be eliminate the t's. Okay. So I'm going to do, just going to get rid of this. I'm going to do equation 1 minus equation 2. Okay. So negative 3s minus 2s is negative 5s. Negative t minus negative t is nothing. 5 minus nothing is 5, and that's all equal to 0. By the time I do all the math on this, I get a value of s that's equal to 1.
Yep.
Yep. Pretty good, right?
Yep.
Okay. How am I going to find out what my value of t is?
You're subbing back in.
I'm going to substitute it back in. Yeah, that's right. And so I'm going to sub s equals 1 into 2. Okay. So 2 times 1 minus t is equal to 0. So t is equal to 2. So I have just verified, or I found out that these two have a common x and y coordinate when s is 1 and t is 2, I have not verified this for the z coordinate yet. So I'm going to have to do that. Okay, so I'm going to set this up. I am going to substitute s is 1 into this, and I'm going to substitute t is 2 into that one, and I'm going to see if I get the same z coordinate. And if I do, then I'm going to know we have the point of intersection.
If what? If you have a value for z?
Well, just watch. You're going to see we'll end up with an x and y and z coordinate for here, right? Okay. So x, y, z is equal to 2, 1, 2. And my s value is -3, 2, 2. Okay. And so,
oh, I get it now.
okay, good. -1, 3, 4. Okay, so line 1, for that value of s, I get -1, 3, and 4. Now, for line 2, x, y, and z is equal to, so -3, 1, -2, plus 2 times 1, 1, 3. Okay, we're looking for the same x, y, and z value here. So -3 plus 2 times 1 is -1. So far, so good. Okay, 1 plus 2 times 1 is 3. And -2 plus 2 times 3 is 4. All right, hooray. It is the same point, okay? So we derived our s and t values. By comparing x and y coordinates only, we had to verify that it's the same z coordinate by testing our s and t values in both lines, and we get the same point. Okay? Definitely intersect, and they intersect at -1, 3, and 4. Okay. Good so far?
Yep.
This is method 1. Method 2 is, in fact, sort of the same thing. But basically, we're taking the parametric form of one equation and we're substituting it into the symmetric form of
I think
another.
I get the parametric form now.
What's that, Johnny?
I think I understand the parametric and symmetric stuff now.
Yeah, good. It'll come in and out, but it'll get to be even better as time goes on. So next week when we're done the course, hopefully it's pretty good. Okay, method 2. Okay, so let's substitute, I don't know. Let's substitute the parametric form over there for x, y, and z into the symmetric form for line 1.
Megan belongs you to the office for pickup. Please, Megan, to the office.
So substitute the parametric form of line 2 into the symmetric form of line 1. And right now that doesn't really tell you what we're actually headed for, but what we want to do is we want to find out what value of t, what the value of t is that is going to find the point of intersection, and we can do that by substituting this symmetric definition for x, the parametric definition for x over here into the symmetric x down here. So I've got x minus 2 over -3 equals y minus 1 over 2. Now I'm going to take this definition, I'm going to substitute it for x. So -3 plus t, that's my x, minus 2 over -3 is equal to, and now I'm going to substitute the parametric form over there, 1 plus t, that's my y, minus 1 over 2. I'm going to simplify the top of this expression a little bit. So t minus 5 equals t. And this one's over -3. That one's over 2. Now I have to do my magic, cross multiplication or whatever you want to call it. 2t minus 10 is equal to -3t. And so I wind up with 5t is equal to 10. So t is equal to 2. Now you might recognize, yeah, that happened before when we did this, okay? And it does because we're using the same line, which is kind of unfortunate. Maybe in another way. When I compare my x and y, I get this value of t. I have to check and make sure that my z is going to work. And so I'm going to compare y and z exactly the same way. Okay, so that is y minus 1. Oh, I'm not totally sure what the z is. Oh, but I can figure it out from here. That is z minus 2 over 2. Okay, so I'm comparing the symmetric form of y and z over here, and I'm going to be just substituting these parameters for y. So 1 plus t minus 1 over 2 is equal to -2 plus 3t minus 2 over 2 for my z, as long as I've done that right. Okay. What we're looking for is the same value of t, and hopefully t ends up being 2, because if it doesn't, oh, that means we've done something wrong somewhere in here, but we can probably fix that. Okay. So this is simplifying the top. T over 2 is equal to 3t minus 4 over 2. And so this becomes, doing my magic cross multiplication, multiplying both sides, 6t minus 8. And so I don't know. Let's move the t's over to the left side. -4t equals -8. I wind up with t is equal to 2. Okay. So the x and y are the same for that value of t, and the y and the z are the same for that value of t. And so yes, they intersect. That's method 2. All I really have to do now to find out what the point of intersection is substitute 2 in for t into any form of the equation that I like, okay? So I could put a 2 in for t up here, and I'm going to find out that what the point of intersection is exactly the same as before. And so those are our 2 methods for finding intersections, okay? Once again, in tooth space, we're already familiar with how everything works. Basically, you almost always have lines that intersect. Sometimes you have lines that are parallel. Sometimes you have lines that are coincident, okay? And the solutions look a little bit different. In 3 space, we often have this thing that might look like it intersects until we rotate it. Okay, so we're always checking to see if these are skew lines. Similarly, we could have parallel lines in 3 space. Okay, and if they're parallel lines, we can probably pick it up based on the direction vector, because they're going to have the same direction vector. Similarly, in 3 space, we could have lines that are totally coincident with each other. Okay, and so that is that.